Welcome to my channel. After about 5 months, I'm back, and today's video will be on Urysohn's lemma, a result from gender topology, first course in gender topology. Your teacher might have said, and Monkra's book very clearly says, Urysohn's lemma is perhaps the first difficult result in the course, right? And more than that, it's highly original. Okay, we will talk about it as is my usual way of doing things. We will look at it little more leisurely way, why it is important, what it tries to say, etc., and try to put it in the context. Don't be in a hurry to jump into the proof directly. Okay. If you follow this thoroughly and revise it at least once later, you will see almost you can be confident without much preparation, you will be able to give the proof on your own. Okay. I'm confident of that if you put your mind to this. Okay. So let us get started. And just one thing, many times people write to me about, this my videos, they are unable to find, etc. How many times I can keep repeating? Please download the Excel sheet, which or the PDF file, which is consists of all the playlist in in the order, topic wise. For topology course, for linear algebra course, for metric space course, for measure theory, real analysis, everything, there is a separate thing. Please download and see that. Okay, you can see that it is already given. You may download the list of videos on my channel here. Search for list of videos. List gives the description, links of videos, and the videos are arranged in order of preferred order of viewing. It will also be periodically updated. Okay, please do that. Don't waste your time. Okay, right. Now the reference is for this lecture is going to be a book by Vikram Maital and myself, a topology of core course, especially sections 4.5 and 5.2. Yeah, right. I forgot to screen share. Okay, there, right. So let me just go back. Please download from this. Look for the list of videos. Okay, then it will give the videos description, the URL, the links, and also it gives the specific order in which you can read. Okay, you can watch. Okay, so let us go. So the major thing in topology is the so-called separation axioms. As far as I am concerned, okay, in a core concept, there are only three things. One is Hausdorffness, separation axioms. So there are, for me, there are three. First one is Hausdorff axiom, Hausdorff property. You know what it means. If you give me 2 points x and y, x not equal to y, there exists disjoint open sets u and v, such that x belong to u, y belong to v, and u intersection v is empty. That is, this means you can separate. One usually says you can separate two distinct points. By open sets. So this is the way you should learn it. This definition is okay for every pair of points x and y with x and y not equal, x and y distinct. There exists disjoint open sets with this property. Okay. The second thing is regularity. That says if x is a point and A is a closed set such that x is not in A, then there exists open sets u, v, u intersection v is empty. Sorry, is empty, open sets, such that x belong to u and A is contained in V. That's it. That means you can separate a point, a closed set, and a point not in it, not in the set, by open sets. The third is normality. So I will not waste much time. We are assuming A and B are disjoint closed sets. Then there exists U and V disjoint open sets, so that A is contained in U and B is contained in B. That means you can separate two distinct, not distinct, disjoint closed sets by means of open set. Disjoint closed sets by open sets. Okay. So these are what I call set theoretic separation. Means okay, or topological separations. But there is a very interesting thing. This is what is not emphasized in usual topology book. That is, you want to separate them by means of real valued continuous functions. Okay. If you had watched my lectures on metric space, you would have seen that. Even in points of topology lecture, some places I have mentioned this also. But to keep this more or less self-contained, it's good, and also to put everything in context, perspective, it's better to learn them again. Okay, we will do that now. Okay, what it means is I want to know whether there exists, that is separation by means of continuous function, real valued continuous function. What does it mean? For example, let's look at Hausdorffness. You gave me 2 points x and y, x not equal to y distinct point, then whether there exists a continuous function f from x to r, continuous, such that fx is not equal to fy. For example, I can assume fx is 0, fy is 1. Whether there is such a continuous function. Okay. And similarly, regularity, I can say that if x is a point not in the closed set A, whether there is a continuous function f from x to r continuous, so that fx is, let us say, 1 and fy is 1. Fx is 0 and fy is 1. That is, you are separating. Okay. Why this is called separation? That's again clear. I have, let us say, 1 here, 0 here. I can take minus 1/4 to plus 1/4, and here 3/4 to 5/4. Right? These are all open sets. Call this as u1 and v1, and let u equal to, if, since f is continuous, f inverse of u1 will be open set, f inverse of v1 will be open set, and x belong to u, y belong to v, and by construction u intersection v is empty. And same thing here also. Are you following? And same thing with this. These are disjoint closed sets. Okay. Then there is whether there is a continuous function f from x to r, such that f is 0 on A and 1 on B. This continuous function. Right? And when it comes to this closed thing, you know, there is in topology they have a word for this, completely regular spaces. So if it's a completely regular space, it's a regular space. That is, I can separate a point, a closed set, and a point not in the closed set by means of real valued continuous function. So for example, here I can perhaps call it completely Hausdorff, and here I can call it completely normal. Okay, pause, review. So the general topology course, in the beginning what it tries to do is, it tries to separate points and sets or two sets or whatever it is with the extra conditions, okay, by means of open sets. But for analysis and real purpose, what you really require is to separate them by means of continuous function. In the context of regular spaces, there is an analogous notion, completely regular, which simply means a closed set and a point not in that are separated by means of a real valued continuous function. So one should ask for analogous questions in the case of Hausdorff's condition, and similarly in the case of two disjoint closed sets. Okay, then I can call completely Hausdorff completely normal, like in analogy to completely regular. Is that clear? Yeah. The interesting thing is Urysohn's lemmas. Yeah, before I say, but there are examples which show a Hausdorff space need not be completely Hausdorff. Remember, completely Hausdorff space is automatically Hausdorff. Completely regular space will imply it is regular. Completely normal space also will imply it is normal, as I have seen that, right? Take f inverse of minus 1/4 to 1/4 and 3/4 to 5/4. Okay, then they are going to be disjoint open sets as you wanted. Correct? So, a completely Hausdorff spaces Hausdorff, completely regular spaces regular, and completely normal spaces normal. One can ask whether the converse is true. There are examples. A Hausdorff space need not be completely Hausdorff. A regular space need not be completely regular. Let's not worry about it, okay? But in the context of normal spaces, Urysohn lemma says a space is normal if and only if it is completely normal. Do you understand this? That is the significance of the result. Okay, let's go back. Let us state the theorem and try to understand. So Urysohn's lemma says a topological space X is normal if and only if there exists a continuous function. If and only if for every disjoint closed sets, every pair of disjoint closed set A and B, there exists a continuous function f from X to R, so that f is 0 on A and f is 1 on B. Right? So if such a continuous function exists, we know it is normal. We had already seen that. Okay. So the Urysohn's lemma, the significant, the hard part of that is, if X is normal, there exists a continuous real valued function as stated. Yeah. Right. Notice that this is the difficult part. Just to think about, you will understand the highly creative original proof of Urysohn. What do you have? You have only a set with some topology. You call it a normal space. You have nothing else. From this data, you want to construct a continuous function, continuous related function. Of course, given two disjoint closed sets A and B, you want to construct a real valued continuous function. Okay, it's something amazing. Okay, to explain again, to put it in context, let us try to understand. In the context of metric spaces, it's extremely easy. Why? Because when the moment I say it's a metric space X, there is a real valued function not on X, perhaps on X cross X to R. Right? So if I freeze one of the variables, I will get a real valued function from X to R, and it's also continuous. In fact, it is a jointly continuous, but that's immaterial for our purpose. From that, I can construct continuous functions as required. Again, if you have gone through my metric space, you would have understood these things. Okay, but To put it in context again, I'll quickly go through it, then we'll turn to the issue. So suppose XD is a metric space, okay? It comes with a metric which a real valued function on not on X cross R. So if I freeze one of the variables, keep one variable fixed, it's a function, continuous function on the other variable. Okay, this is continuous, is very known, well known. Okay, very well known. So let us say, suppose I want to, you know that metric space is Hausdorff. Now I want to know whether it is completely Hausdorff. Suppose you give me a point x not equal to y, then let me define a function f of y. Let me call it a and b, a not equal to b. So okay, let me define a function f of x equal to f of x and distance between x and a. Right? Then what is f of a? 0. What is f of b? F of b will be distance between a and b not equal to 0. So if you want, I can divide it by distance between. What can you define? I want it to be 1. Right? Therefore, I can divide it to be b and a. Right? When x equal to a, this will be 0. When x equal to b, it will be 1. And it's very easy to check this is a continuous function. So any metric space is actually completely Hausdorff. Similarly, for regularity, suppose I have a point P and a closed set A, P is not in A, right? Let us look at the function f of x, which is defined to be distance between x and A. Okay, this is by definition GLB of distance between x and A as A varies over A. I will not go into that. Look at my videos on metric space or my book on metric space, or again on the topology book. It will have this thing. This is a continuous function, right? Now if P is not in A, f of P is not 0. F of P is distance between P and A, which is positive, whereas f of x is 0 for all x in A, right? Therefore, I have separated. If you want 0 and 1, a very trivial manipulation will give you, okay? And in the case of Hausdorff, normality also is the same thing. Suppose A and B are closed sets, and A intersection B is empty, then you have defined the function f of x equal to, I don't want to motivate all those things. And B, okay? Then you can see f of f is 0 on A, and f is 1 on B. Because if it's not in x is in B, this is positive, this is 0, this is the same thing, therefore it will be 1. You understand? So in the case of metric space, okay, the Hausdorff is completely Hausdorff, regularity is completely regular, no, it's normal, completely normal. And in particular, Urysohn's lemma is obvious. Why was it possible? That's because you already have some kind of a function, if not on x cross x, to R, which is continuous. In fact, it is bicontinuous, continuous in both the variables. Right? That made our life easy. Now you understand why Urysohn's lemma is something fantastic. You just have a set and a structure topology, and it has some special property called normality. Somehow I have to construct a real valued function, and that too it should be continuous. Finally, it has to satisfy the condition. F must be 0 on A, F must be 1 on B. You see that? Just you enjoy. Okay, this is fantastic. Okay, how did Urysohn do it? I do not know how he got, but let us work backwards. Now that he has done it, we will try to understand it in a better way. Okay, so that our life becomes easy. Let us look at it. As many of you know, one of my standard tricks is work backwards. Okay, we know the result is true, then go backwards. Understand? Okay, the same trick I am going to do that will make Urysohn's lemma easier. The proof will be easier to understand. In fact, it will be easier to recreate if you had gone through this at least once or twice and revised it in your mind. Okay, we'll do it now. The result is, suppose I have, let us look at a function from R2 to R. I'm going to look at only simple, whatever I'm going to do could be any topological space also, I can do that. Okay, right. And let's assume it's a continuous function, right? Then the function, suppose you see is in the image of your, then let us look at f of C. This is set of all points xy such that f of xy equal to C. Okay, this is called a level set of f at level C. Okay, why it is called level set? Easy example is, suppose f of xy is y, then f inverse of C is nothing other than y equal to C. If C is positive here, if C is negative, C is here. So this is the level set. This is your f inverse of C. Right? Okay. And this is called sublevel set. That is set of all xy so that f of xy is less than or equal to C. For example, in the case of our fxy equal to y, our sublevel set will be this. This will be your, let us say, yes, f of C, sublevel set of f at C. So this is your S of C. Do you understand that? Yeah. Now there are very nice things about this. First, notice that this is a closed set. Okay, S of C. We can see two things. Okay, let me see S of C is less than. Instead of this, let me just make it. Therefore, this line is not included. This is just a dot, 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 dot. This is an open set. And if C is less than D, then S of C is contained in S of D. Okay, if this is my D, this will be my, all this below will be this. Right? Not only that, something interesting happens. Okay, these are all open sets. Okay, next, yes, F C closure is contained in S F D if C is less than D. Right? So what you have done is the space R2, okay, I was stratified. This is a word. Stratification is another word for level. Okay, okay, these are the strata. This is called a strata. Okay, a strata or level. Stratum, singular word, or level. Okay, so my R2 is stratified. These are all my strata. Right? In such a way that something interesting happens. What happens? Each SFC is open, and if C is less than D, SFC closure or SFC is contained in SFC closure, or get this, and that is contained in SFD. Is that okay? Right. So, what have we got now? So, what have we seen? Notice that the whole thing can be done for any real valued continuous function on a topology space also. Okay. So, given a real valued continuous function on R2, Rn, or any topological spaces, we have a stratification of the entire space, right? And with some very interesting property that also is clear, right? We define what are called sublevel sets S of C. They are all open, and their closures are contained in S of D if C is less than D. Is that clear? Now, what is the question I want to ask? Suppose I had given the stratification, can I recover the function f? Is the question clear? Yeah. Now I do not know function. What all I know is, let us say SC is given. Okay. What is C? C is a real number. SC is a subset of, open subset of X. And said that for C less than D, SC closure, the closure of SC is contained in SD. Okay. This family is given. Now the question I can ask, whether I can recover the function f. Does there exist a function f which induces this stratification? Is the question clear? Pause, review, proceed. So, question is the following. And of course, the stratification must be this. Is given, okay, does there exist a function f x to r which is continuous such that f inverse of c, or rather x such that fx is less than c equal to s of c. Okay, pause, review, proceed. Let me make sure I'm sharing the screen. Yes. Okay. The answer is yes. Now suppose I take a point. Let us look at only this case R2 to R to have an idea where f of xy is y. Now suppose I have a point xy. Right? How do I say, okay, how do I define this? Okay, there are, now don't say this is y, okay. If you have a space x and these are the stratification, okay, and what I have, one side this is your C, something intuitively I am drawing, right? How will I get that C? There are two ways, okay. Look at the function, all those things, okay. Let us look at SC. Let me just check. What do I want? Let me collect my thoughts. See, the easier way will be, there are two ways of doing. So let me just see which will be easier. Fx is less than or equal to C. Let us look at, right. So let us look at this. So we have this. Okay, these are the things. My point, or maybe in R2. Okay, this is my point. Call it x naught, y naught. Okay, and these are the SC. Right? To recover, what we need is look at all C so that x naught, y naught belong to C, SC. That is point xy so that fxy is less than or equal to C. So this will all be here, all this kind of thing, right? So what we want is the one which is the infimum. So we define f of x naught, y naught to be equal to the infimum or GLB of C so that x naught, y naught belong to SC, right? So we are defining fx naught. Thus we have got a function from R2 to R by this thing. So of course one has to show it is continuous, right? This is the very general method we want to do that. This way we are able to define a real valued function. I do not know whether it's continuous or not. It can be proved. That's what my reference, okay, the book which I gave as a reference contains a proof. Is that clear? Now something is tangible. What is tangible? If I want to prove Urysohn's lemma, what it says is that I have to get some kind of stratification by means of open sets. With what property? The union must be all of x, and if the stratification should be parameterized by real numbers. Okay, let us call it C. Then such that for each such C, SC must be open, and if C is less than D, SC closure must be contained in SD. If I could get such a stratification, I can define a function, real valued function. Then I would prove it is continuous. Is that clear? Yeah, right. But we can simplify the work. First, have you understood? Just pause the video for a while. Think about. Don't worry about. Okay, just to get intuition idea what is happening. We are going to actually put it in. Okay, in precise terms. Okay, is that okay? But we can actually implement. Make it easy. Suppose instead of a stratification by means of a real number, suppose I do a stratification by means of rational numbers. That is, for each r in rational number, I have stratification SR, which is SR is open, such that SR closure is contained in ST, where R is strictly less than T. Right? Suppose I get it. Do you think I can still do that the same way? Because supremum or infimum of the rational numbers, okay, of an interval, and it is intersect, and the supremum or infimum of the interval intersect with Q, they are the same. So I will get a real valued function. Do you understand? Are you following? Okay, let me just, if you need, I will just do a thing. See, if I have AB, okay, let us say supreme or I usually LUB is same as LUB of AB intersect with Q, and similarly GLB, right? Therefore, it's enough if I get a stratification SR for R and Q. Just so what needed was density. But I could do something better. Let us look at dyadic rationals. They are of the form m by 2 to the power n, okay, where m and n are integers. Okay, this is dense. So, for each r here, if I do something r in q, so that SR is contained in SR closure, which is contained in ST, if R is less than T. And R and T are dyadic rationals, call it D. Right? I can still do the same trick. Yeah. So, this is what we want to do. So, what we plan to do is for each dyadic rational in the interval 0, 1, okay, because our final real valued continuous function will from x to r will be actually in the interval 0 to 1. It will take values in the interval 0 to 1. That's it. Therefore, we are looking at only dyadic rational in the interval 0, 1. For each dyadic rational r, we will define an open set SR in the normal space S. Okay. With what property? SR is open and union SR is all of x, and if R is less than T, SR closure will be contained in ST. Okay. Then I can define a function, real valued function, as we looked at the previous example, and then I have to prove it is continuous. And the way we constructed will make sure F will be 0 on A and it will be 1 on B. Is that idea clear? Okay. I will stop here. We will continue. Okay. We will execute this idea in the next one. What is the key result in that? Though there is only one key observation we need it. I will say that, and with that I will stop. Okay, the key idea is the following lemma. Let X be a normal space. A, assume non-empty, of course, not necessary, non-empty closed set. And U open set such that A is contained in U. Then there exists an open set V such that A is contained in V and V is contained in V closure. V closure is contained in U. Yeah, most of you would have seen the result, but let's give you a quick proof if you want. Okay, what is the proof? Proof is let B equal to X minus U. Then it's a closed set, and A and B are disjoint. Correct? Yes. So the picture is this is my X, and this is my A. This is my U. Right? The complement is my B. Right? So A and B are right. Therefore, because of normality, since X is normal, that implies there is open sets, disjoint open sets. V, W, V intersection W is empty, and A is contained in V, and B is contained in W. Is that okay? Right. Now let's look at V intersection W is empty. That means V is contained in W complement, that is X minus V. This is a closed set. Yeah, correct. Therefore, the closure of V, which is the smallest closed set containing V, that is, it is the intersection of all closed sets containing V, right? Therefore, V closure is contained in WC. Is that clear? But look at what is W? W, B is contained in W. Therefore, B complement contains W complement, that is U contains W complement. Therefore, W complement is contained in U. Alright. So, what have you done? I have produced an open set U. So, there is closure. That means let us give a picture again for that. This is my open set V. So, that V closure is contained in U. Is the proof clear? Now, you can see I can keep on doing this. Okay. If I have a closed set, I'm sorry, I forgot to screen share. So the whole thing is lost. The key is let X be a normal space, A be a non-empty closed set, U be an open set that A is contained in U. Then I want to say there is an open set V so that A is contained in V and V closed is contained in U. The trick is this is the picture. Okay, define B to be the complement of U. That will be closed set. This is right. Now what do I do? Since X is normal, this set A and B are closed set, they are disjoint. Therefore, there exists open sets U and V. And such that V intersection V is empty, A is contained in V, B is contained in W. Right? Now, V intersection W is empty, that means V is contained in W complement. Right? But since B is contained in W, B complement, which is U, that contains W complement. Right? Are you following? Therefore, V closure is the smallest closed set, intersection of all closed sets containing V. Right? Therefore, V closure is contained in W complement. right? But W complement is contained in U. Why? Because B is contained in W, therefore B complement contains W complement, but B complement is U, therefore U contains W complement, therefore we prove the result. Okay, pause, review. That's a very trivial lemma. This I would actually call it an observation, but it's a fantastic observation. This is the one which is going to give us for each diadic rational how to build a family of what do you call a stratification based on this diadic rational in 0. Do you think I have whetted your appetite for a proof? Okay, we'll continue later. Okay, this is the basic idea. Now you will see the proof comes very fast. Once the idea is clear, it comes really fast. And the interesting thing is, we stick to diadic rational, therefore, the proof becomes much more transparent than the usual proof which uses density of Q, density of rationals. Instead, I am using density of diadic rational to do this proof. Okay. This is not very popular, but it is gaining popularity using diadic rational in place of rationals. Okay. We will see that proof soon after this. Okay. Stay tuned. We'll meet again.